Hello, and welcome to this section of the Physics 3 tutor. In this section, we're going to cover the topic of orbiting charges in a magnetic field. And we're going to have a few sections here because here I want to outline sort of the theory, and the following sections will work some problems to really show you what we're talking about. You might guess that since the title is orbiting charges, there's going to be some information about something orbiting, and that's exactly right, so your intuition is correct. Now, remember from the last couple of sections, we spoke a great deal about the fact that when you have a magnetic field, right, present, and you shoot a charged particle into that field, the magnetic field doesn't really speed up or slow down that charge. It doesn't push it along the direction of motion like an electric field does. But what it does is it exerts a force that's perpendicular to the velocity of that particle and also the perpendicular to the field itself. So what it basically does, and we drew a few pictures, is it causes the charge direction to change. It causes it to curve, right? And so that's something that's just always going to be the case when you deal with magnetic fields and charged particles moving through a field. Of course, if the charge isn't moving at all, then there's no force at all, so nothing really happens, which is also different than an electric field. Now, one thing that I did not tell you previously, I kind of hinted to it. I told you, hey, you have a particle, you shoot it in a field, it's going to bend, right? What I didn't really tell you is that if you just have a magnetic field in space, which, you know, they're always around. There's a magnetic field right now in this room. There's a magnetic field in deep space. If it's unobstructed and it's just present, and if I take a charged particle like an electron or a proton or some heavy ion or something, and I shoot it into that magnetic field and I observe it, what's going to actually happen is that particle is going to move and it's going to begin to curve, but if you watch it long enough, it's going to begin to kind of go around in a circle over and over and over and over and over again. And it turns out that we cannot see these magnetic field lines, but if we could, right, if there was a magnetic field that was going like this, and I shoot some charged particles from me to you, they're going to begin to go and basically orbit the magnetic field lines, basically, because that's the way the forces are going to actually line up. So what I want to do is prove that to you, not with a bunch of math, but with a bunch of pictures, so that you can understand why that's the case. So let's go and do that. Let's pretend that we have a magnetic field coming out of the board. It's coming from me to you, so it's coming towards you. All right, and what we're going to do is label some instant in time, time 1, because what I'm going to have is a few snapshots in time that I'm going to draw, and I'm going to try to show you that what I'm saying here is true. So what we're going to have is I'm going to represent it as a dot, and I'm going to put B vector under it. This dot means that there's a magnetic field. The dot means it's coming towards you, right? Of course, if you ever see in a book an X like this, that means the magnetic field's going away from you. But in this case, we're saying that the magnetic field's coming toward you. Now, this magnetic field there might be tons of magnetic field lines all around here, but I'm only drawing one of them for clarity. Okay? Now, let's look at time 1, and let's pretend that we have a particle up here, some charged particle, and it has a charge Q, right? And let's say that here at the beginning, this particle is actually moving this direction. So what I'm doing is I'm drawing a velocity vector, so I'm going to put V bar, right? So what we have is a situation where we have a magnetic field. Of course, the magnetic field's everywhere. It's uniform, but I'm only drawing it in one location here just for clarity. But the field obviously exists at all points in this board. It exists right here where the particle is, on top, on bottom, if I could draw it, I would draw a bunch of dots everywhere. All right? So you have to use your imagination a little bit because of the way I've drawn this thing. But if there's a velocity this direction, now remember, the length of the arrow, the particle's actually here. The arrow is indicating the direction this particle is actually moving. Like maybe we have an electron gun here and we shoot an electron in. We take a snapshot. At this point, it's moving this direction with a certain velocity, so many meters per second. What is going to be the magnetic force, the force exerted on the particle by the field at that point, at that time? What's it going to be? Well, it's going to be, if you remember, the magnetic force is always QV cross B. So all we need to do is figure out the cross product to find the direction, to find the cross product between V and B. So here's V. B is coming straight out of the board, the magnetic field. So imagine it being a vector right like this. I'm using my marker to represent it because it's a little bit easy for you to visualize it coming out of the board if I stick it right here. So if I stick it right here, if I'm going to cross V into B, I'm going to take my right hand, I'm trying to come kind of out of the board, and I'm grabbing V and I'm crossing into B, so my thumb is pointing down. Convince yourself that that's true. So there is a force on this particle actually acting down, FB. This is the force. All right? So what's going to happen? If we do that, we shoot the guy in there, then the magnetic force is actually going to be acting toward, down a little bit. So that's snapshot in time number 1. Let's look at time 2. Right? So let's try to get time 2 and figure out what's happening there. So I'm going to redraw it. I'll try to be a little bit quick about it so we're not spending all day with this, but it's very important. So we have B. All right, and my particle is now in black. So let's say what's happened is we started up at the top here, and what's really happened is the force has kind of bent the curve down. Let's take the next snapshot in time here. The next snapshot, because the force has kind of bent the curve path, changed the path of the thing down to here. Now, of course, here's Q. All right, and of course, at this point, since I've bent the path down, my velocity vector is here, like that. Now, where's the force going to act? Well, again, let me try to help you out visually. Magnetic field is coming out, so I'm going to put the magnetic field here, right? And if you can use your imagination with the right-hand rule, you got to cross V into B. So grab V, grab B. The force, again, points towards the center. So there's a force acting this way, FB. So now this is interesting. We start out here, we shoot it, obviously perpendicular to the magnetic field, and there's a center pointing, when I say center pointing, it's pointing to this reference point here, of magnetic force. So that bends the path of the particle this direction. Now we look at another snapshot, and again, the force points to the center. I'm going to draw a few pictures, but what's going to happen is it's going to continue pointing to the center no matter where you are on this circle. And that's what's going to keep this particle going around and around and around and around, basically. Let's prove that and make sure that's true. So let's go and take a look at time 3, right? And I'll speed things up a little bit since you kind of know the punchline. So here we have, actually let me change colors just to make it consistent. So we have, this is our magnetic field. So everything's the same with regard to that. Magnetic field's not changing. Now the particle originally started up top, but it kind of got pushed because of the center-seeking force here, and then we're also noticing at that point we also have a center-seeking force, so it's kind of bending it this direction. So let's take another snapshot here, Q. All right, now the velocity of this particle, since we bent it around, is pointing this way, and if we take B being out of the board again, at this, because it's uniform, B is everywhere, right here, then let me label this real quick. This is velocity V. Then we need to find V cross B. So if you get your right-hand rule and like that, cross V into the B that's coming out of the board, you're going to get a force that's pushing up. So I don't have enough room to draw the arrow taller, but this is FB. Okay? So again, no matter where we are, the force is not pushing the particle along its velocity vector, it's pushing it inward, like that, kind of perpendicular, bending the course of it the whole time. So let's look at time 4. This is so important to particle physics and lots of different branches that I really just enjoy doing this because it's so much illustrative of what's going on. So here's a magnetic field. Particle originally started at the top. We bent it around all the way down. Of course, when we got to this point, the force was still pushing it up. So we got to this point. Now I'm going to draw another reference. That's supposed to be a Q, like this. And of course, since we bent it around, the velocity is still going this direction. Let me help you out. With a B here, how is V cross B going to look? If you try to cross V, grab it first into B, you're pushing again towards the center. So what you're going to have is a center-seeking force like this. And we'll do one more real quickly at time 5, like this. Then what we have is magnetic field here. Nothing has changed. The particle originally started at the top. So we found that the particle started up here. The center pushing force has curved the path all the way to the bottom. We get here, it continues curving it this direction. And when we get here, it continues curving it, and guess where it lands? All the way back to where it started. And when it gets all the way back to where it started, it's coming this direction. The velocity vector is exactly equal to what we started with before, because conservation of energy, it's going to come back to exactly the place that it was. Nothing is lost. We're pretending there's no losses in this system. And if we take the magnetic field to be out of the board, we're going to get the same result. When we cross them, the center seeking force, FB, is there. So there you go. You start here at the top, and you put energy in, and what ends up happening is you curve the path down, you curve it around, you curve it up, and you curve it right back to where you start from, and assuming there's no loss in the system, the particle will keep orbiting round and round and round and round again. So it's like a little miniature solar system that's really going on there. And this happens anytime, basically anytime you have a magnetic field and you shoot particles into it. They're always going to go in circles. That's basically what happens. I could have told you that last section, but it gets confusing without drawing all of these pictures to show you how it happens. So in the last section, in most of the physics books, the way they introduce them is they say, look, here's a magnetic force. It's QV cross B. The force at any time is the cross product between V and B. Of course, you got to multiply by the charge. That gives you the direction of the force. So it's going to bend the path. Usually that's sort of like stage one to kind of show you what's really happening. But in practice, anytime you have a constant magnetic field and you shoot a particle into it, because of this business going on, you always have the charged particles orbiting round and around and around and around and around. That's just fact. I'll draw some pictures in a minute. That's happening in the Earth's magnetic field out in space with the solar wind that's coming in from the sun, hitting the Earth's magnetic field. Those particles hit the magnetic field and they start orbiting the Earth's magnetic field lines, going round and round and round. Now, of course, you can't see magnetic fields with your eyes, but if you could put on special glasses and just look at the particles, you know, and if there's a field here, you can't see the field, but if you just look at the particles and zoom in, you'd see little bitty, all of them orbiting, you know, all over the place, basically. And that comes from this magnetic force that's acting around and around. All right. Now, what we want to do, since we understand this motion, it's going around and around, it would be nice to understand a little bit more about it. For instance, how fast is it going around? How long does it take one orbit? What is the radius of one of these little bitty orbits of an electron that's going around and around? What's the period? What's the frequency? How fast are they moving? That kind of stuff. So I could just list all of those equations. They're very simple equations. How to calculate the radius, you know, this radius here, how to calculate that, because it's all going to depend on the charge, on the magnetic field strength, and a few other things as well. I could just give them to you. But the derivation is so incredibly simple, and it really gives you an appreciation for how it's done, that I'm going to just go ahead and derive it really quickly for you. So we're going to take it one step at a time, and you'll totally understand this. So what forces govern every particle in motion? You have to ask yourself, what equation governs every particle in motion? In classical physics, anytime something's moving and there's a force acting on it, F equals ma is always applied. So that's what we're going to start with. We're going to start with F is equal to ma. F is equal to ma. Now the question you have to ask yourself is, F we kind of understand. The force acting on this is the force that's the magnetic force. So we already know what that's equal to. We'll plug it in a second. That makes sense. But what accelerate, and the mass is the mass of the particle that's going around in a circle, right? But what is the acceleration? What does that mean? Because we already said that the magnetic field doesn't actually speed up or slow down the particle. It doesn't push it faster, faster, faster. It doesn't accelerate it in the typical sense, right? But what it's doing is it's changing the direction. So think back to your basic physics and your basic vectors. An acceleration is defined to be a change in velocity. Changing velocity. Now there's two ways you can change velocity. One is if you're going down a racetrack, for instance, you could step on the accelerator and push yourself faster, faster, faster along that direction. That's a rate of change. It's changing your velocity. That's an acceleration. But more broadly, a change in velocity is also when you change the direction of your velocity, right? So if you're going around a racetrack, is a great example, and you're not changing your speed, you're going a constant 60 miles an hour, or a constant so many kilometers per hour, but you're constantly racing around a circle, right? You know from experience that your body is kind of thrown out and there are forces going on there, and there's a centripetal acceleration because of the fact that you're curving your motion. So in other words, what I'm trying to say is acceleration comes from two places. The first one is if you're going straight, then you can accelerate by changing your speed, just speeding up, slowing down. That's the thing we usually think about. But it's also equally valid that you're changing your velocity anytime you change the direction of this velocity vector. This is a vector. The length of this arrow, I haven't been perfect, but I've tried to keep it the same everywhere, but the direction is different. Therefore, an acceleration has occurred. What kind of acceleration is that? If you take a baseball on a string and you start whipping it around, right? So it's orbiting your hand, right? It takes a force to do that. You have to pull. You have to give tension on that rope to get it to do that, right? You kind of do this as a kid. You got to get a feel for that. So you can feel yourself pulling on that, and even though it's not the typical definition of acceleration we think of, it is accelerating. There's a center-seeking acceleration called centripetal acceleration that we've learned about from Physics 1. That is what's going to go in here, because we're not changing the speed of the thing, we're changing its direction of motion. Therefore, it is accelerating, kind of a center-seeking acceleration. All right, so what is the force? This is the force of the magnetic field, so I'll label it FB, right? What is that equal to? FB, because of the way we've drawn this, we're deriving it in terms of how we've drawn it, the velocity and the magnetic field are already perpendicular to one another. So the general thing is FB is obviously QV cross B, right? But if everything's already perpendicular, then you don't really have to worry about a cross product. You can just look at the magnitude of the force, which is QVB sine of the angle between them, right? We've already talked about this. This is if you just care about the magnitude of the force, which is all we care about here. But the angle between V and B are already 90 degrees. You've got, no matter where we're at in this picture, you have a velocity this way and a magnetic field coming out of the board. So the angle here is already 90 degrees. So really, for practical purposes in this particular derivation, the magnetic force is the charge Q times the velocity of the particle times the magnetic field strength. None of these are vectors anymore because I only care about the magnitude. That's all I care about here when I'm doing F is equal to ma. So what I'm going to really show here is that this magnetic force is Q times V times B, right? This is the charge of the particle that you're going around in a circle with, the velocity of the particle times the magnetic field, equals. The mass is going to stay. That's the mass of the charged particle. What do we do for A? A is centripetal acceleration. That's the center-seeking acceleration anytime you have something going in motion around something. And that's exactly what we have here. If you look back from Physics 1, the centripetal acceleration is V squared over R. V is the velocity, the speed, I should say, the speed that you're going around in that circle. R is the radius. So R is the radius of this guy. If you go back and flip to your Physics 1 material, or if you go back and review my Physics 1 DVD, you'll see that centripetal acceleration, forget about all this other stuff. Centripetal acceleration is always equal to V squared over R. If you know the speed of the thing, you know the radius it's traveling in a circle, that's a centripetal acceleration. So this is a valid equation. F equals ma is always valid. This is the force acting on the particle. This is the mass of the particle. This is the acceleration of the particle. So there you go. So now what we want to do first is solve for R. So let's do that. Let me just move R over here. So R will equal mv squared over, let me move all of this stuff to the other side, QVB. So all I did was take R, move over there, and divide by and get all this stuff like this. Now what do we have? We have a velocity on the top, or actually a velocity squared on the top, so I'll strike through the squared and I'll strike through the velocity on the bottom. And so what we really have at the end of the day is R is equal to mv over QB. This is the radius of motion. What this tells you is that if you're in a lab, right, and if you create a constant magnetic field of so many Teslas, and you shoot a particle in with a charge of so many coulombs, that's what's going to go in for this Q here, and that charge has a mass of so many kilograms, and you shoot it in with a velocity of so many meters per second, then all you have to do is put those numbers in here and divide, and you're going to get a number, which is going to be in meters, and that's going to be the radius of this motion. So if you actually could get a microscope and see everything, then what you're going to see is a circular motion, round, 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 forever and ever and ever and ever and ever and ever and ever, and the radius of that motion is going to be basically what I've drawn on the board. That will be this radius right here. From if you could look at the total circle, it would be from the center of the circle to the path. That's the radius of the motion, mv over qb. And of course, if you put in coulombs, teslas, kilograms, meters per second, you're going to get meters in terms of your radius. So that's huge. You definitely want to know the radius of a circulating charge. Now, another thing that's very useful to know is when you're studying circular motion, how long does it take to make one complete circle? How long does it take to make one complete circle? That's called a period. The period of motion is one period. How long does it take to go all the way around? You know, the Earth has a period of 365 days to go all the way around the sun. What is the period of one of these electrons or something that's orbiting a magnetic field line? Well, the period is usually denoted T, right? And the way you would calculate it is you would look at what is the circumference of the circle that it's basically traveling on, divided by its velocity. Because if you think about it, this is going to be meters, a unit of meters, divided by meters per second. Meters are going to cancel, seconds are going to flip up to the top, and you're going to have a unit of seconds. So you want to know the total distance it traveled divided by the speed. That's going to tell you how long it takes to actually happen. This is the total distance you traveled around this circle over here, divided by the speed. So what would the circumference be in this case? What would the circumference be? Well, it's a circle, right? So circumference is going to be 2 pi r over b. All right, so the period is going to be 2 pi, but we just found r. We know what the radius of the motion is because we just calculated that. So we'll just stick all this stuff in here. mv over qb. This is the radius. We'll divide all this stuff by the velocity. Okay? We'll divide all that stuff by the velocity. Now when you look at what we have, this velocity is going to cancel with this velocity. So at the end of the day, the period is going to be equal to 2 pi m over qb. 2 pi m over qb, and the unit here, I should say this is the period in seconds, right? So this is obviously meters, because it's a unit of distance, the radius, I should say, and this is a period in seconds. So again, if you're in a lab and you shoot an electron in, you're going to know what the mass of the electron is. You're going to know what the charge of the electron is. If you know what the strength of your magnetic field is, then even if you can't see the motion, it's going to tell you how long it takes one of those electrons to complete one orbit. That is what we call the period. So the period's 2 pi m over qb in seconds. Now, in addition to the period, anytime you talk about the period of something, you're almost always going to also want to talk about the frequency. Period and frequency go hand in hand, right? Period is how long does it take to go all the way around there. Frequency is very similar. It's how many times do you complete an orbit in 1 second, right? That's the unit of hertz. How many times does it go around in 1 second? So, mathematically, we've learned this in previous physics lessons, the frequency is always equal to 1 divided by the period. So all we have to do is go 1 and divide by t that we've defined here, and so if we do 1 divided by this quantity, all that's going to happen is this quantity is going to flip over. So the frequency is qb over 2 pi m, and the unit is hertz, which just means how many times do you complete an orbit in 1 second. So qb over 2 pi m, that's a unit of frequency. And finally, the last thing that we want to talk about sometimes in some problems is we want to talk about the angular frequency. Instead of the regular frequency, the angular frequency. The angular frequency we've talked about in previous classes, Physics 2 tutor, for instance, is 2 pi times the regular frequency. Basically, this frequency, it's just two different ways of saying the same thing. So don't get so wrapped up in what's the difference. It's just two different ways of saying the same thing. One of them is how many times can you go around in 1 second. The other one is kind of calibrating it. So we have 2 pi radians in a full circle, right? In terms of your trigonometry, right? You have 2 pi radians in a full circle. So it's basically finding out, telling you how many radians do you cover in a second, basically. Because if you're traveling this many times around the circle in 1 second, you multiply by 2 pi, which is a full circle, you're finding out how many radians do you travel in 1 second, which is kind of an angular measure, which is useful for some things. So all you do is 2 pi times f. We already know it's 2 pi times qb over 2 pi m. Now look what happens here. This actually gets simpler because the 2 pi is going to cancel with the 2 pi. So what we really know is that the angular frequency is equal to qb over m. And the unit here is radians per second. qb over m, radians per second. Now I want to stop here and kind of recap what we've learned and give you a few notes so that you'll understand how to use these things, and obviously we'll use them on our problems as well. So we have a situation where I've taught you that anytime you have a uniform field and you shoot particles into it, those particles are always going to orbit. If you could see the magnetic field coming out of the sun and the solar wind, you would see tons of stuff orbiting. It's just the way it is. It's because of the fact that this force here always acts perpendicular to the velocity of the particle. So naturally, anytime we're talking about circular motion, we want to know what the radius of the motion is. We just look at F equals ma. This is the magnetic force. This is the centripetal acceleration. We solve for the radius. This is the radius that all of these particles are going to orbit at. Notice that it depends on the charge of the particle, it depends on the magnetic field, it depends on the mass, and it depends on the velocity that the thing is shooting at. All right, the next thing we want to know is the circumference. So we just take, I should say the period. We just take the circumference, how far does it travel around, divide by its velocity, and then we get the period. So we know its circumference, 2 pi r. We use the previous result, divide by the velocity. This is the period of motion. The frequency is 1 divided by the period, and then the radial frequency is, or the angular frequency, is 2 pi times f, 2 pi times the regular frequency there. So there's a couple notes I'd like to let you know here. I want you to realize that the period, the frequency, and the angular frequency are actually independent of v, the velocity of the particle. That's pretty amazing when you think about it. You would think that all of that stuff would be dependent on how fast I shoot the electrons in or whatever. But when you look at it, the period of motion actually does not depend on the velocity. So if I just barely tiptoe an electron into the chamber, it's going to have a certain period of motion, right, with a certain frequency and all that stuff. If I get an electron gun that shoots it like near the speed of light in the chamber, you would think, oh boy, it's going to be going a lot faster. Everything's going to be different. Well, if the mass of the particle is the same, the field is the same, and the charge is the same, the velocity can be anything, but the period of motion is going to be, the period of motion is basically going to not change, no matter what speed you actually shoot the particles in. That's pretty amazing when you think about it. But the radius of this guy does depend on the speed. The radius does depend on the speed. So what we have here is a situation where, I'm going to say this 2 times because it's really important. If you have a magnetic field and you have 2 different electrons you're shooting in, one, you're barely tipping them in there, and the other one, you got a giant electron gun shooting them in at 50 million electron volts or something super fast, right? What's going to really happen is the particle that's going in with very slow speed is going to have a really small, because it's very low velocity, it's going to have a really small radius, really tight radius. If you have the particles shot in at a super high energy, really, really, really fast, those particles are going to have a very large radius. They're going to be orbiting big time around those lines, very large radius, but they're traveling really, really fast. So those 2 effects kind of cancel so that the period of both of those different electrons is exactly the same. The slow electrons orbit really, really tiny, but they're going really, really slow, right? So the fast electrons are going really fast, but they're taking a really long path around orbiting this guy. So what happens is they actually take both of them the same exact amount of time to make one orbit, which is the period. That is the punchline, all right? And that's kind of an intuitive thing that you can't really predict ahead of time until you look at the equations and really start thinking about what they're telling you. The next thing I want to tell you is in this equation we have v here, velocity. In fact, I've used velocity all over the place here. Don't forget what this is. When we talk about velocity and you're doing these calculations, you're really talking about the velocity perpendicular to the magnetic field. Perpendicular. So here's the magnetic field. I'm pretending that I'm shooting an electron in perpendicular to the field. That is the velocity that I care about. I'll come back, circle back around to why that's important in a minute, but in all this entire setup, I'm basically trying to make sure you understand that you have a field, I'm shooting a velocity in exactly perpendicular. That's the speed that I'm actually putting in these equations. The other thing is I've got Q everywhere. But because I was always dealing with an absolute value of the force, it doesn't really matter if Q is positive or negative for these calculations. If you put a, for instance, if you put a negative Q in, if it's an electron, you're going to get a negative radius. That doesn't make any sense. What you're really trying to do is put the absolute value of the charge in, and that's giving you the radius that you have. But what you will find, and what I'll talk about here in a few minutes, what you will find is if you have a different sign charged particle, all of these numbers are going to be the same, but it's going to orbit in a different direction than the positive particle. So the positive and the negative particles, they all behave and observe these laws. You can calculate the frequency and the period and the radius and all this stuff, but obviously they're different particles, so they're going to have different directions. They're going to orbit in different directions if they're positive or negative. But for the purpose of these calculations, you're trying to calculate the radius, just put the absolute value of the charge in there.